Good morning, all. We'll be in the finishing stages of shipbuilding material.
Good morning, sir.
Starting with steel, you have mild steel, medium steel, high carbon steel, high tensile steel. We'll be doing all those. First, we'll do what is cementite and perlite, which are the transformations taking place due to the temperatures, heat treatment, the how the transformation takes place. Now, in a steel, you have carbon added to iron, so that forms iron carbide or cementite, and your cementite lies with the iron molecule side by side. When the cementite has got pearl-like appearance, it is known as pearlite. So iron carbide or cementite is a compound of iron and carbon. So it is basically having a formula of Fe3C because carbon is surrounded by iron molecule, those atoms, to form a molecule of Fe3C. So by weight, your carbon is 6.67%, iron is 93.3%. Now the crystal structure is orthorhombic. Orthorhombic is because there is a center, you have carbon surrounded by iron atoms, like these. So you have the center, you have carbon surrounded by iron atoms. That is orthorhombic. Now cementite is thermodynamically unstable. So if you heat it, it will change. The temperature where it changes is known as eutectoid temperature, where your change of the appearance takes place. So it will be converted eventually to austenite with low carbon level and graphite with to high carbon level depending on your temperatures. So it does not decompose on heating at temperatures below eutectoid temperature or metastable iron carbon phase. So eutectoid temperature is a temperature after which the change takes place. So it is the minimum temperature at which your material exists as a single solid solution phase, or when you are alloying the elements completely soluble in matrix phase, that is eutectoid temperature. So cementite, if you cut across, you will have this kind of grainy appearance. Now perlite is another form of iron with your it appears has a pure pearl-like appearance like this, not a pearl-like appearance, rather than the cementite which has got porous appearance. So pearlite is a two-phased lamellar structure composed of alternating layers of ferrite and cementite that occurs in some steel and cast iron. And during slow cooling of your iron carbon alloy, the pearlite formed by the eutectoid reaction as your austenite cools below the temperature of eutectoid, that is 727, or depends from iron to iron what kind of eutectoid temperature is there. So pearlite is a microstructure occurring in many common grades of steel. This has come once or twice. What is pearlite? Differentiate between pearlite and cementite in your exam. Previously, 4 5 years back, this has come pearlite and cementite. So transformation of pearlite to austenite takes place at lower critical temperature of 723, and from cementite to pearlite will take at high temperatures. So at the temperature, pearlite changes to austenite because of nucleation process. This is pearlite. Now we'll come to what is austenite. Austenite is the appearance is like this. So the austenite appearance is like this. So it is a gamma phase iron in a metallic non-magnetic allotrope. of iron. So this allotrope of iron, your cementite, perlite, all are allotropes of iron. Like you have allotropes of carbon as graphite, diamond. These are all allotropes of carbon. So austenite, cementite, perlite, these are all allotropes of iron. Austenite is non-magnetic. It is metallic but non-magnetic. So it's a solid solution of iron with alloying elements. And in plain carbon steel, this exists above your critical eutectoid temperature of 723 degrees Celsius. So other alloys of steel have different eutectoid temperatures. So your eutectoid temperature depends on which alloy of steel you are handling. So eutectoid temperature is where your change takes place after you heat it. Because will be doing heat treatments. So there the changes takes place due to the heat treatment done above a eutectoid temperature or below a eutectoid temperature. So austenization means to heat the iron or iron-based metal or steel to a temperature where it changes the crystal structure from ferrite to austenite. So here you are heating to a phase where it changes from ferrite to austenite. Ferrite is magnetic, austenite is non-magnetic. So we've done brittle fracture, malleability, tensile strength, fatigue, wrought iron, cast iron, all the features we've done. Now I'll be doing what are the types of steel and what are the types of tests of the steel. Then we'll finally do the heat treatment. Now your types of steel, mild steel or MS, whatever you is MS is mild steel. So mild steel is generally used in shipbuilding, while medium steel is not used in shipbuilding because cutting and welding becomes difficult for it. But mild steel, your cutting welding is easier, so here you use it for all your structures. So it has got a low carbon content, so that means it is tough. So your steel is mild because you're using mild carbon. Medium carbon will be medium carbon steel, and high carbon steel has got tough your hardness. When your carbon content is low, you can make it tough, but you can't make it hard. So if your implements you have to make those which you have to make it hard, the carbon content has to be more. So mild carbon steel is used for beams, plates, bars, stringer plates. All those plates are made of mild steel. So your iron is containing small percentage of carbon. It's strong and tough, but it is not hard. So your tempering cannot be done. We'll be doing the tempering after this. So tempering is a heat process of making it tough. Like you have tempered glass on your mobile. So tempering is a heat process to make that glass tough so that it will protect your mobile screen. So this mild steel is also known as plain carbon steel or low carbon steel. This is malleable, it is ductile. The tensile strength is not much. You can't pull it too much. But in shipbuilding, you have to use material which is cheaper and easier to form because you can't make your shipbuilding cost very high. So mild steel is generally used in shipbuilding. Now in application in shipbuilding, for application we have done that steel to be considered. We had earlier done what are the properties of shipbuilding material. It should be carbon content should not be more than zero point 0.3. So mild steel is containing carbon content 0.15 to 0.23, which is good for shipbuilding. So it has got reasonably high manganese content to make it tough. The sulfur and phosphorus are always kept less than 0.05 because otherwise they'll explode while welding. So here your sulfur and phosphorus contents of mild steel will be less than 0.05 because high contents can hamper welding properties and cutting properties of steel. So your other applications will be steel frame buildings, scaffoldings, your machinery parts, your cookware, your pipeline, your fencing, your metal gate, all will be made of MS steel or mild steel. So your floors in the pump room or in the engine room are made of mild steel. These are your angles made for mild steel, or your longitudinals made of mild steel. Your girders, this is a girder, T-shaped girder made of mild steel. Bars made of mild steel. So that's the uses of mild steel. So here you have nuts and bolts made of mild steel, your fences, your car body made of mild steel. So your this is a structure gantry crane. So it's mild steel, ductile and malleable metal. This can rust quickly, so you have to paint it. It is used in nuts and bolts, building girders, car bodies, gates. Melting point here is 1600 degrees Celsius. Now we come to medium carbon steel. Now, medium carbon steel is not typically used in ships. It is basically used for your, can be used certain like crankshaft, you can use or for the gears, you can use, but engine room you can use, but not in deck enough. So mild steel's got a carbon range of more than 0.3, so that is 0.31 to 0.6. Manganese content is 0.06 to 1.65. It is stronger than your low carbon steel, but the formation is difficult. Welding is difficult, cutting is difficult. So here you can't use in shipbuilding because you require a lot of welding and cutting there. So medium carbon steel is quite hardened because your carbon content is more. Then it is tempered to make it tough by using heat treatment. So this is used for railway track because it can take load, railway wheels because they can take load, crankshaft of your cars, of your ship, of your other bodies, crankshafts, the gears, machinery parts requiring the combination of the properties. So here you have the train wheels, crankshaft, and the railway track. These are all made of medium carbon steel. Carbon content is 0.3 to 0.6, can be heat treated. Austenization can take place. Quenching, that means sudden cooling of steel after heating is known as quenching. Then you can temper it. This has got low hardenability. You can add chromium, nickel, and molybdenum to give it a better shine, better heat treating capacity. So these heat treated alloys are more stronger, but they have low ductility. So your applications of medium carbon steel will be railway wheels, tracks, gears, and crankshaft. This is a crankshaft which you see. Now we come to high carbon steel. So this is your high carbon steel. So the carbon content is high, so it is hard. So you have ball bearings, chisels, punches, hammer, all made of high carbon steel because they have to be hard. If you just hit a hammer, you can't just get it bent. This has to bend the other thing. So this is hard. Now your carbon content here. So in all your short notes and all, you have to write the carbon content, manganese content, all those contents you have to write. Can't just miss out. This you have to remember. What is the carbon content? What is the manganese content? What is the sulfur content? What is the phosphorus content? Sulfur and phosphorus content will be same 0.05 because you can't have explosion in welding cutting. So high carbon steel will contain carbon content higher than your medium carbon steel, which is zero point 0.3 to zero point 0.6. Low carbon steel or MS steel will be, mild steel will be less than zero point 0.3. High carbon steel will be 0.6 to 1%. The manganese content will be 0.3 to 0.9. So this you use for springs, for insulation, for fire bulkheads, in reefer tanks. There you use this high carbon steel. So it's used for spring materials, high strength wires, insulation for fire resistant divisions, for reefer tanks insulation. So it's good wear resistance. And it was also used for cutting tools like chisels, hammers, high strength wires, and it's got finer microstructure that improves the toughness of the material. So here you have high carbon steel, which can be harder than carbon steel, but this is more brittle. So here you heat treat it to make it harder and tougher. So you temper it, make it hard and tough because high carbon is there, so it's hard. But if you just use it, it's going to break. So to reduce your breakage, you make it tough by heat treatment or just tempering. Ball bearings, these are pretty hard. Chisels, punches. Now, in certain areas on ships where you have high stresses or where you hog and sag a lot, that is your garboard strake, your keel plate, your shear strake, regions where you have high tensile, very high stresses, which is a hog and sag, there you have fittings of high tensile steel. So it is a low alloy steel that can withstand maximum strain without failing or breaking or getting deformed. The yield strength is pretty high, that is 50,000 to 1 lakh pounds per square inch. Carbon content is high, which is zero point 0.6 to zero point 0.8. Sulfur content, if you see in all steel, will be 0.05 or less than equal to 0.05. So all your steels, you can write your sulfur and phosphorus content same, 0.05 or less. Manganese content will change, silicon content will change. So manganese content here will be 0.6%, silicon 0.2. So strength of the material is the capacity to oppose force, weight, or stress. The strength of mild steel is quite less compared to strength of high tensile steel. The thickness of mild steel used will be much thicker as compared to high tensile steel because high tensile steel can take a lot of stresses. So the flaw here is if your high tensile steel gets rusted, the strength of that will be reduced because your thickness will be reduced. So it's got a greater tensile strength for equivalent thickness even at low temperatures, used on large tankers, BLOCs, and denoted by H for your various grades of steel. You have A grade, B grade, C grade steel. There you are having H. So H is your high tensile steel. So high tensile steel is used for mechanical engineering applications like your shafts, rotors, other engine parts that are continually being placed in stressful areas or heated conditions. It's got very high yield point. It's got a reduced plastic ductility and brittle fracture behavior is quite less as compared to mild steel. So this is your high tensile steel plates. So this has come a lot in your exams. What is high tensile steel? What are advantages of high tensile steel? What are disadvantages of high tensile steel? So the first disadvantage is reduction in scantlings. The scantlings are the shipboard construction material used of various sizes on ships. So like you have your stringer plate, your girders, your strakes, your longitudinals, all are basically scantlings. Your beams, all these are, and your floor plates, all are scantlings. So when you are reducing in scantling, that means your light ship weight is going to reduce. Because these plates are thinner as compared to mild steel, so the weight will be less. So your light ship weight will reduce. So if your light ship weight is reduced, you can load more cargo because your displacement will be same. When you reduce your light ship weight, your dead weight will increase. Third point is your greater tensile strength even at low temperatures. So steel can crack at low temperatures. So here you have been given a heat treatment for greater tensile strength even at low temperatures. They've got extremely high strength and stiffness as compared to mild steel. Now the disadvantages of high tensile steel. Now high tensile steel thickness is, let me explain with this diagram how the thickness will change the strength of the material. Now, suppose this is your high tensile steel, your thickness of mild steel is this much. So, this is mild steel. This is your high tensile steel. So, this will give the same strength, this thickness. Now, suppose a corrosion occurs and the corrosion is maybe 10%. 10% here, maybe a little more corrosion. So, corrosion has occurred here, and I'll make this red here. Your steel structure is this much. So now this is your high tensile steel, this is your mild steel. So because of your corrosion level, your thickness will reduce, your strength level will reduce with the corrosion. Let me mark it out. So your high tensile steel strength is reduced as compared to your mild steel once it is corroded. So that's the disadvantage of your high tensile steel, because as it is, your thickness is less. So once the corrosion sets in, your thickness is reduced, your strength is reduced further. So this is one of your disadvantages of high tensile steel. So after corrosion, there's a reduction in thickness. In your exam, if you make a diagram like this, it will, you can score more. So better to explain with diagrams, because I'll impress your examiner and he's going to give you better marks. So after the corrosion, the reduction in thickness of HTFs as a percent of original thickness is greater, thus leaving the plate weaker than the ordinary MS plate. Second disadvantage is reduced scantling, because you're reducing scantlings. That can prove dangerous for the strength of ship in the long run. And the high density of high tensile steel can invoke brittle fracture. So these are the three disadvantages of high tensile steel. Now we come to the destructive test, which is normally asked in your exam. Why are they destructive tests? Because the sample piece is destroyed. It's maybe stretched to the point of destruction, or bent to the point of destruction, or pressed to the point of destruction, or impacted to the point of destruction, or compressed to in fatigue test, or in temperature increase and to break it. So that is all to the point of destruction. So first we will do the tensile test. So in tensile test, sample piece is kept here. Can be vertical, it can be horizontal. So this is the length overall here. This is the area where it is grip. The gripping is taking place in the vise. So this is the width of grip section. Once it is pulled, the necking will take place. We've done your tactile fracture, the necking. So once it is pulled, the necking is going to take place. At the point where the necking starts is known as shoulder. So that where the necking, the point where the necking starts is the shoulder. So this is the distance between shoulders. Where the necking is parallel sides to each other, that is known as gag length. And here is a reduced section. So at what point the stretch takes place and the crack starts and the brittle fracture, they have to know. So what is the strength required to pull and break it to the fracture point? So that is your tensile test. This is all destructive test. You have to draw a diagram like this. You don't have to draw, you can draw this diagram also, but best if you draw this diagram. So this is carried out in a tensile test machine. So load is applied hydraulically to draw apart the ends of the test piece till the point of destruction. There you determine your stress strain curve, that is your elongation, yield point, limits of proportionality, UTS. You can determine in your tensile test because you're finally fracturing it at the fracture point or the breaking point. So tensile strength is maximum load being applied to the original cross section area. Original cross section area will be this. This will be a reduced cross section. So this is the original cross section area. So the maximum load being applied divided by original cross section area. The second destructive test is bend test. Now, if this is the rod here, you have two supports here. These two supports. This point, this weight here, that is mandrel, because you are pressing the rod against this point with a load being supported by the supports. So you're pressing this here so that your bend takes place like this. Now this point here, this area, this section here, the surface here, are checked very closely for cracks. At what angle of bend the cracks will appear? That is checked. That's why the bend test. So normally you try to make these two sides parallel, or angle A, maybe you try to maximize or make it 180 degrees. But the crack can occur earlier also. So this alpha, not angle A, alpha is the angle of bend being done. So now let us come to the points here. So A is your thickness of your maybe rod. The length of the rod is L, capital L. These two are supports. Distance between these supports is L, small l. This is the mandrel which is pressing the rod to bend it. So the diameter of the mandrel is D. So now this is pressing downwards. When it is pressing, the rod is being bent like this. You try to bend it to make these legs of the rod parallel to each other. So the angle between the or angle of bend is alpha. You observe at what angle of bend the cracks will appear. If the angle of bend is more, that means you can bend this kind of rod more. If the angle of bend is less, that means you can't bend it. It's going to break earlier. So the test bar or plate is bent around 180 degrees till the ends are parallel, as I've explained in the diagram. So the bend area is closely inspected for cracks or fracture. So you determine your ductility and soundness of metal. Determine your bend test, fracture strength, resistance to fracture. So these characteristics can be used to determine whether a material will fail under pressure, and therefore it's important for construction purpose, because there you require ductile material for bending. So how much bending you can do on that material. Now shipbuilding Your plates have been bent in your bilge areas. So if you can't bend it, it is not going to pass the bend test. The third test, destructive test for your steel or shipbuilding, is hardness test. So suppose you are putting your hand on the bonnet of your car and putting your weight there, maybe the dent will occur. So that is indentation on the car bonnet because you're applying a constant force there. Here also you're applying a constant force of hardened steel bar or iron carbide ball. Here the carbon content is pretty high to make it hard. Like you have ball bearings. Ball bearings are pretty hard. Then the type of ball is used for pressing against that metal surface to see how much indentation it can withstand at constant force. So indentation is here. You're going to press it. If it's a very hard material, the indentation will be less. With a soft material, the dent will be much bigger. So the dent is known as indentation. So if F is a continuous force being applied on the ball or the hardened steel ball on the test specimen, you see what is the diameter of the ball vis-a-vis what is the diameter of the indentation. So the indentation will be formed here. If your indentation is small, that means it's hard. Indentation is bigger than your diameter of the ball. That means it is a soft material. So the load test is applied to dent the surface of the metal and you determine your ability to withstand wear and tear. So here the indicator number is Briley number. Like you have pencil. कितने एचबी पेंसिल है वो हार्ड पेंसिल. So Briley number is indicator of hardness. It is a load in newtons divided by area of indentation in millimeters square. So Brinell hardness test consists of indenting the test material with a 10 millimeter diameter hardened steel or carbide steel ball and is subjected to a load of 3 tons or 3000 kgs. For softer material, you can reduce your load to 1500 kg or 500 kg to avoid excessive indentation. So the full load is applied normally for 10 to 15 seconds. And in case of iron and steel, for at least 30 seconds in case of other metal. So diameter of indentation left is checked with a low powered microscope. So Briley hardness number is calculated by dividing the load applied by the surface area of indentation. अभी जरा इस पे रोक लगाते हैं एंड आपके जरा वीडियो देखते हैं टेंसाइल टेस्ट एंड बेंड टेस्ट ये सारे वीडियो जरा देखते हैं. So 9 minutes, 8 minutes now. The rest 3 we'll do in the next class. I'm not doing it very fast so that you understand. Because you have the time now. Not that you don't have time. You've got ample time.
The Brinell hardness test. Using the Brinell method, the hardness of a turbocharger housing is to be measured. First of all, the tester has to make himself familiar with the testing machine. A monitor and the control panel are positioned in the upper part of the machine. These are used to select and program different testing methods. Below the control panel, a microscope lens with a digital camera and an indenter are installed. These two elements are connected to each other and rotate towards the test piece as required. It is also possible to select and exchange the indenter, so different methods of hardness testing can be conducted on the same testing machine. The support table can be adjusted in height, so the test piece can be positioned at the correct distance to the microscope lens and the indenter. After becoming familiar with the machine, let's start the experiment. The principle of the Brinell hardness test is to press a hard spherical indenter with an exactly defined force onto the test piece, then evaluate the surface area of the indentation. The tester selects a suitable spherical indenter and inserts it into the holding device of the testing machine. Next, he puts the turbocharger housing onto the support table, rotates the microscope lens into vertical position and adjusts the correct height of the test piece. After bringing the test piece surface into focus, he selects the exact spot where the hardness test is to be made. By pushing the start button, the hardness test procedure begins. The machine rotates the lens back to its resting position and places the spherical indenter carefully on the test piece surface. Gradually and shock-free, the test force rises to its specified value. After maintaining the test force for a certain time, the indenter automatically lifts off again and the microscope lens pans back to its former position. The indentation can now clearly be seen on the monitor. With the control knob, the tester places 4 measuring lines on the edges of the indentation to measure its diameter. That's it. The testing machine can now calculate the Brinell hardness. The hardness value is defined as test force F in the old unit kilopond divided by the area of the indentation A in square millimeters. The result is displayed on the bottom left-hand corner of the screen and amounts to 250.
Now this is
Okay, now we'll have a break. Tea break now.
Okay, sir.
So good afternoon. We completed your tonnage now. Load lines and tonnage we've completed. So we'll start from
Good
scratch
afternoon,
now.
sir.
Shipbuilding material. So we'll be coming to your stress, strain, and modulus of elasticity and all that we'll be covering now. So the definitions now we'll be doing is tensile strength. That means it's the amount of tensile stress a material can withstand before it breaks or fails. It is also a measurement of force required to pull something, such as wire or rope or a beam, till it breaks. So you have three types of typical definitions for tensile strength. You have yield strength, you have ultimate strength, and you have breaking strength. So yield strength means the stress a material can withstand without permanent deformation. So it is in the elastic phase only because your permanent deformation is in the plastic stage. So yield strength is not a sharply defined point, and that is a stress that will cause permanent deformation of 0.2% of original dimension. Your ultimate strength is the maximum stress a material can withstand, and breaking strength is the stress coordinates when the material will rupture or fail. So this is 2% deformation is the yield strength here. Ultimate strength will come here, and break point of the fracture is where it breaks. So these are the definitions, the various definitions of yield strength, ultimate strength, and fracture. Basis tensile strength. Now, what is ductility? As you remember, you're pulling a wire, pulling a copper wire, or from copper you're pulling a wire, so that is ductility. So anything which can be elongated like to a wire, that is aluminum wire, copper wire, or gold, which is into very thin wires. So it is the measure of degree of which the material can strain or elongate between the onset of yield and eventual fracture under tensile loading. So it is the extent to which a bar will stretch before it ruptures, and that is the measure of the metal's ductility. It can also be expressed as percentage elongation. So I'll show you the diagrams here. A wire being pulled from copper, so that is ductility. So it's a physical property of material which can be stretched without breaking. And the examples here are gold, silver, copper, erbium, terbium, and samarium. Now we come to malleability. So malleability is a property when a metal can be beaten into sheets, like you have aluminum foils, gold foils, silver foils. So that is example of malleability. So it's an ability to be hammered, pressed, or rolled into thin sheets without breaking. So it is a property of metal to deform under compression and take a new shape. So the substance ability for deforming under pressure known as compressive stress. So a material may be flattened into thin sheets by hammering or rolling, which is again malleability.
So the gold is the most malleable metal. That's why it can be used in making ornaments. Here you have aluminum foil, which you use for packing your food material. So malleability is the property of substance that can be bent or hammered into thin sheets without breaking. Aluminum is very malleable. That's why you use it for wrapping food. Glass is not malleable. Wood is not malleable. Copper is malleable. Now we come to hardness. We are all doing that because we'll be doing the various tests. So there is a difference between hardness and toughness. Hardness means constant stress you're putting on a material. So what action will it happen on the surface? Suppose you're putting ball bearing on a surface and pressing continuously, maybe for 30 seconds. That is the test of hardness. You're suddenly hitting on a metal, that is known as toughness, like your collision. So hardness is the resistance of material to localized deformation, which can also apply to indentation, scratching, cutting, or bending. So certain metals are harder than others, like plastics, wood. So macroscopic hardness can be known by strong intermolecular bonds, and the hardness can be basis scratch hardness or nail hardness. That means you can't scratch on a metal or a car. So that is scratch hardness. Indentation hardness, you can't make a indent or from your ball bearing, you can't make an indent, or a rebound hardness. Rebound hardness is also known for your mattresses. When you sit on it, it is going to rebound. So hardness is depending on ductility, elastic stiffness, plasticity, strain, strength, toughness, and viscosity. Now, if you have this chart here, this is Mohs hardness scale. On top, you have diamond, which is scale 10. Next to it is corundum, which is a scale of 9. Then you have masonry drill bits, which is 8.5. Topaz is 8. Quartz, you have 7. Steel nail is 6.5. Orthoclase is 6. Knife or glass plate is 5.5. Apatite is 5. Fluorite is 4. Copper penny is 3.5. Calcite is 3. Your fingernail is 2.5. Gypsum is 2. Talc, with which you make talcum powder, is 1. Now we come to the definition of toughness. So toughness is basically how the metal will react to sudden force, sudden impact. You're hitting by a hammer, that is sudden impact. So how does the material react under sudden impact? So it's a resistance to fracture of a metal or a material when stressed. Or it can be defined as amount of energy which can be absorbed before the material ruptures. Second definition can be area underneath the stress strain curve, will also define the toughness. Third definition is the work required to deform 1 cubic inch of metal until it fractures. So it is the ability of a material to resist the start of permanent deformation plus the ability to resist shock or absorb energy. So if you see this metal, this is a brittle metal. So the area under this curve is less because the fracture point is here at B. The fracture point of this ductile metal is at B dash. So the area under this curve is A, C, C dash, B dash. It's a big area. That's why this is much tougher than this metal. So toughness, the ability to absorb energy up to fracture. That is energy per unit volume of material. So tough material will have both strength and ductility. So you have that area under the stress strain curve here, which measures the ductility of this material. Sorry, the toughness of this material. This is a ductile material, so it is quite tough because the area under this curve is quite large, so this indicates the toughness of a ductile material than of a brittle material. Now, if you're hitting a material on the clamps, this is not breaking, so that means it's tough. This is breaking, so it is brittle. Now, you have instances of vessels sinking down maybe in 2 minutes after breaking down. And that brittle breaking can be an event of brittle fracture, because the energy absorption and the speed at which this fracture occurs without warning can be 2,133 meters per second, very fast. So the entire ship can crack and sink within minutes. That is the reason we got to be very careful about this brittle fracture. This occurs because of loss of ductility when you go into sub-zero temperatures and your steel is not treated well. So brittle fracture can occur and the ship can sink in minutes. So it is a fracture of a metal caused by lack of ductility due to low temperature. So it is a sudden, very rapid cracking of an equipment under stress with little or no evidence of ductility or plastic degradation before the fracture occurs. So you don't have warning sign for this fracture. It occurs very suddenly. So in brittle fracture, no apparent plastic deformation takes place before fracture, and it involves little absorption of energy, but the speeds of occurring this fracture is very high, 7,000 feet per second, and in steel, and this will continue even if your loading is discontinued. So little fracture of normally ductile steels can occur in large continuous box-like structures like box beam, pressure vessels, tanks, pipes, ships, bridges, or other restraint structures. And this fracture can occur in service, which is initiated by defects that were initially present in manufactured stage, or it can develop during service. Now, the types of brittle fracture can be either transgranular or intergranular. So that depends on whether the grain boundaries of the material are strong or weak than the actual grains. So a transgranular fracture is a fracture that follows a crack through the lattice in the granular material and ignores the edges of the grain in individual lattice. So it will go through and through. So this kind of fracture will be smooth and the sharp edges will not be there because it is going at the through and through the lattice. So the cleavage or cracking in most brittle uh, now this cleavage occurs by repeated breaking of atomic bonds across your specific planes, and this fracture splits the through and through the grains. You see, the cleavage is on the red line, so it is not going on the edges, but through and through the grains. So this is transgranular fracture. Second type is intergranular fracture, where your crack will occur around the grain boundaries of the material, which become weakened due to the cleavage. So your breaking will be on the grain boundaries here. So that breaking point will be on the grain boundaries here. That is intergranular fracture. So brittle fracture, if you see, surface looking very sharp, very smooth here. So brittle fracture takes place without any appreciable deformation by rapid crack propagation, which can go up to 2133.6 meter per second. And the direction of crack motion is nearly perpendicular to the direction of applied tensile stress. So this is your stress and this is your strain. Epsilon is basically your strain and sigma is your stress. So when the gradual tensile load is applied on a material in a tensile test, that means you're pulling it, the end of your elastic limit without prior indication, the material will break, and that is known as brittle fracture. Now, we'll also do ductile fracture, which happens when your material is pretty ductile. So if you have brittle fracture, it will go like this. The shape will be like this. So that is the original specimen. So brittle fracture will have normal perpendicular to it. While a ductile fracture, because of the pulling, the necking will be done and it will be resulting in this kind of cup and cone fracture. So cup means the inside material comes in this section, that becomes the cone. Cup means it is got an indentation here. So the material inside will come here and this will form a cup, this will form a cone. Ductile cup and cone is typical ductile fracture. This kind of fracture is brittle fracture. So the ductile fracture requires a lot of absorption of energy, and this occurs slowly. While brittle fracture is very fast and the absorption of energy is pretty low. So now we'll do the ductile fracture. So this type of fracture is characterized by extensive deformation of plastic or necking, and this usually occurs prior to the actual fracture. The term ductile rupture refers to the failure of highly ductile material, and in such cases the material pulls apart instead of cracking. So in ductile fracture, an extensive plastic deformation or necking takes place prior to fracture. So your terms rupture or ductile rupture describes the ultimate failure of ductile material loaded in tension. So its extensive plasticity causes a crack to propagate slowly due to absorption of large amount of energy prior to fracture. So if you see the brittle fracture, the absorption of energy is less, while in ductile fracture, absorption of energy is very high. In brittle fracture, the crack propagation is very fast, while in ductile fracture, crack propagation is very slow. So the basic steps in ductile fracture are void formation. There is a void being formed, and the voids join together to form void coalescence. Then the crack propagation takes place, and then you finally have cup and cone shape failure. So the voids or the holes inside or the gaps inside will join together around the precipitates and the inclusions and at grain boundaries. So ductile fracture is typically transgranular, and the deformation due to dislocation slip can cause shear lip fracture, characteristics of cup and cone. So now this is the steps of ductile fracture. You're pulling a material. So this forms a small thin area that is neck. In the neck you will have void nucleation, and then these voids will join together to have void coalescence, and then the crack propagation starts, and then the separation or the breaking occurs in the ductile fracture. Here again you have the necking, void nucleation, void growth, void coalescence, and the fracture. So brittle fracture will absorb low energy, ductile fracture absorbing more energy. Temperature rise will be more here. Temperature rise occurs in low temperature. This will occur in high temperature. So the differences are there. Low strength materials are copper, nickel, mild steel here, high strength material. So your impact energy versus your temperature here. Now the third term is fatigue. So fatigue, if you know, it's a general term that means thak gaya. So material can have thakan, especially when a ship is old. It is subjected to a lot of hog and sag, and with repeated hogs and sag, which are above your fatigue limit, then these repeated alternative stresses can cause cracks. So safety factor above yield strength has to be applied. Since your steel regularly is pushed to yield strength, you will have to suffer metal fatigue. So steels typically have fatigue limit below which any quantity of stress load cycles will not cause metal fatigue or any cracks or failures. So ship design criteria generally assumes all the normal loads on the ship times a moderate safety factor that should be below the fatigue limit for the steel to be used in construction. So your ship should operate in fully loaded condition and strong waves and heavy weather. Your maximum normal design operating conditions many times over its lifetime, provided it is below your fatigue limit. Now, because once your fatigue crack has initiated, it is going to increase with each loading cycle, and the crack is going to continue till it reaches a critical size. So if you stop loading, the crack is not going to continue. In brittle fracture, if you stop loading, still the crack was continuing. In your ductile fracture, crack will not occur if you stop. But in fatigue also, crack will not occur if you stop. But if you still continue loading, the crack will continue to grow until it reaches a critical size. And when your stress intensity factor of the crack exceeds the fracture toughness of the material, then this kind of fatigue crack can have a rapid propagation and typically complete the fracture of the structure. So initially it's slow, and finally the propagation of this fracture is fast. So you have to aid in predicting the fatigue life of a component. So we'll be doing the fatigue test. So you have to do fatigue test. Enhanced survey program also fatigue tests are to be done for ship. And they measure the rate of crack growth by applying constant amplitude cyclic loading and averaging the measured growth of a crack over thousands of cycles to know how much the fatigue has set in the material. So this is the number of cycles, and suppose this is the fatigue limit. So you can do n number of cycles here, but if you cross the limit, then your life becomes reduced because you have crossed the fatigue limit. तो अभी आज के लिए आई थिंक इतना बहुत है. थोड़ा वीडियो दिखा देते हैं बिकॉज लंच टाइम के बाद फिर आपको बोरिंग हो जाता है. लंच से पहले इंटरेस्टिंग है.
आप ही तो दिल की बात समझते हैं सर.
समझते हैं ना, हम समझते हैं भाई. देखो नया टॉपिक है, मैं आपको पढ़ाता रहूं, आप भी करते रहोगे, सोते रहोगे, फायदा क्या है? कोई फायदा नहीं है ना. इसीलिए जरा आराम से पढ़ाएं तो बेटर है. टाइम हमारे पास है. कोर्स हमने आपके अप्रैल वालों का भी कोर्स कंप्लीट हो गया कि नहीं है?
हाँ सर
हो गया, मुझे पता है ना. कोर्स कंप्लीट हो गया अप्रैल वाले का. तो अभी हमारे पास टाइम है, तो इतनी जल्दी भी क्या करें. वीडियो दिखाते हैं तब तक।
This metals. They're all around us. If we knew more about the way metals broke, then the structures of the future could be safer, more efficient, and even less expensive. Hi, I'm Jeffrey Bomarito, and I devote my time to finding out how and when metals fail. Did you know that every block of metal has tons of microscopic voids inside it? And that these microscopic voids actually play a crucial role in failure. When a metal is stretched or loaded, these voids start to grow and link together until the metal fails. If we look at a copper bar being pulled in tension, we see that it behaves the same. In the center region, it necks down until eventually it fails. Now you might ask, what about those voids? How do we know they're the reason for failure? Well, one way we know is by looking closely at the fractured surface. The surface has many dimples, which is a sign that voids have grown and linked together. Now, if we zoomed in on a chunk of metal, it might look like this. If I zoomed in the same amount on a human hair, it would look like this. But if I wanted to analyze this chunk of metal, it would be quite difficult because there are many voids and they're all scattered randomly. In my work, I look at one void at a time, and using a computational model, I look at how it responds to many different loads. I am then able to stitch together the responses of individual voids to understand how the metal will behave on a much larger scale. The simulation you see here is another tension test, where this notched bar is pulled until it fails. One of the very useful things about computational simulations is that we are able to look inside the material to see how the failure process occurs. You can see here that failure occurs as a crack that starts at the center of the member and propagates outward. So, by using a bunch of models of microscopic voids, I'm able to make predictions about how and when larger elements will fail. The truly amazing thing is that these predictions actually correspond to experiments. I'm able to show that damage starts to occur in the center of this element and leads to a crack, which is the same as seen in experiments. The use of computational models such as mine, when combined with simple experiments, will help improve our ability to predict cracks and ultimately help to avoid the failure of our structures. So, as we move into the future, our use of metals will be increasing in efficiency, economy, and safety. If you liked my video and want to learn more, check out my poster on posterhall.org/IGERT2013.
Components which are subjected to loading which varies with time can fail at stresses well below the material's ultimate strength. This is known as fatigue failure, and it accounts for the vast majority of mechanical engineering failures worldwide. The bolts in an office chair, the crank arm on your bicycle, and pressurized oil pipelines are just a few examples of components which are subjected to time-varying loads and may be at risk of fatigue failure. Fatigue failure occurs due to the formation and propagation of cracks. It is a three-stage process. The first stage is crack formation. This usually occurs at free surfaces and at stress concentrations. In stage 2, the crack grows in size. And in stage 3, after the crack has grown to a critical size, fracture occurs. So how can we figure out whether a component is likely to fail due to fatigue? One common approach is to run fatigue tests by subjecting a component or test piece to a large number of constant amplitude stress cycles and counting the number of cycles until it fractures. If we repeat this test a large number of times with different applied stress ranges, we can plot the results on a graph with the number of cycles to failure n on the horizontal axis and the applied stress range s on the vertical axis. Because the number of cycles to failure can be very large, a log scale is usually used for the horizontal axis. By fitting a curve to the data points, we obtain what is known as an SN curve. The SN curve allows you to calculate the number of cycles until a component is likely to fail for a given stress range. For example, if we have a stress range of 100 MPa or 15 KSI, this SN curve tells us that the number of cycles to failure is 500,000. If we know that our component is subjected to 1 cycle per minute, we could predict that our component will fail due to fatigue after approximately 1 year. Fortunately, we don't have to perform these time-consuming fatigue tests ourselves. SN curves for many different materials are already published in different engineering codes. For some materials, and in particular for ferrous materials, it is important to note that the SN curve at a very large number of cycles becomes a horizontal line. This is known as the endurance limit. Theoretically, the component could be cycled at stress ranges below this level forever, and it will never fail due to fatigue. This makes the endurance limit an important fatigue design parameter. It is common to differentiate between high cycle and low cycle fatigue. High cycle fatigue occurs when the applied cyclical stresses are low, and failure occurs after a very large number of cycles, typically more than 10,000 cycles. Because the stresses are low, we are only dealing with elastic deformation. Low cycle fatigue involves higher applied cyclical stresses, and failure occurs after fewer cycles. Because the stresses involved are above the material's yield stress, both elastic and plastic deformation occur. In these cases, a strain-based approach, using for example the Coffin-Manson relation, is usually preferred to the SN curve approach.
Introducing Speechelo, the most natural-sounding text-to-speech software on the market. Hey, I'm Joey, and I'm one of the 30 AI voices from Speechelo. You listened to this video until now and you probably couldn't tell I'm not a real human voice. That's because I understand exactly what each phrase is saying, and I know how to put inflections in my voice, just like a real human would do. I was coded in that way that my neurolinguistic engine will analyze the phrases, and I'll understand when I'm enumerating something, when I have to emphasize a word, or I need to take a deep breath. But you don't have to worry about any of these things. With Speechelo you can generate as many voiceovers as you want with only 3 clicks. Yes, you heard me right. Only 3 clicks. Click number 1. Just paste the text you want to be transformed into speech in our online text editor. Click number 2. Choose the language and voice that you want to use. We offer male, female and even kids voices. And finally click number 3. Click on generate and in 5 seconds your voiceover is ready to be downloaded. How cool is that? And you didn't have to pay a single cent. And didn't have to wait a week to receive your voiceover. We offer voices that are perfect for training videos, voices that are perfect for presentation videos, and voices that sound like Hollywood movie trailers, and even kid voices that sound joyful and innocent. All our voices have elements that make a voice sound real, and
If we return to the data from our fatigue tests, we can see that there is a large amount of variability in the data. This is typical for fatigue tests, even when identical test pieces are used. If we use a best fit SN curve, as we have done here, there is a significant possibility that our component will fail at a much smaller number of cycles than the curve predicts. This test piece, for example, failed at a much lower number of cycles than predicted by our SN curve. For this reason, SN curves published in engineering codes are normally shifted downwards by a certain number of standard deviations to give a reduced probability of failure. Here, by shifting the mean curve down on the vertical axis by 2 standard deviations, we have reduced the probability of failure from 50 to 1%. Fatigue tests are usually run for the constant amplitude fully reversing cycles you can see here. The same stress magnitude is applied in tension and in compression. Let's define a few terms. The stress range is defined as the difference between the maximum and minimum stresses. The stress amplitude is defined as half of the stress range. The mean stress is the average of the maximum and minimum stresses. In this case, the mean stress is 0. But this is only one very specific type of loading. In some cases, we might have a mean stress which is not equal to 0, as shown here. This mean stress will have an effect on the fatigue life. A tensile mean stress will typically result in a shorter fatigue life. One way to account for a tensile mean stress is to use SN curves derived for specific values of mean stress. But these are often not available or would be time-consuming to obtain. Another approach is to use the Goodman diagram, which adjusts the endurance limit to account for a mean stress. Let's see how it works. On a Goodman diagram, the mean stress is shown on the horizontal axis, and the stress amplitude is shown on the vertical axis. A straight line is drawn between the endurance limit at a mean stress of 0 and the material ultimate tensile strength at a stress amplitude of 0. If our cyclic loading conditions are located below the Goodman line, our component will be safe from fatigue failure. There are a few different variations of this diagram, as you can see here. This approach can only be used to determine whether a component will have an infinite life. It doesn't allow us to calculate a fatigue life. In many real-world cases, the applied loading is likely to be far more complex than what we have considered so far. We can use techniques like the rainflow counting method to simplify a complex stress spectrum into a number of simpler, constant amplitude cycles. Miner's rule allows us to account for the cumulative damage caused by each of these different constant amplitude stress ranges. It calculates the damage fraction D as the sum of the fatigue damage contributions for each stress range. The individual contributions are calculated by dividing the number of cycles by the number of cycles to failure for that stress range. The damage contributions from all stress ranges are then summed. If the total sum damage fraction is greater than 1, fatigue failure is considered to have occurred. In this example, the damage fraction D sums to 0.94. This is less than 1, and so fatigue failure has not occurred. If the structure we are assessing contains an existing crack, the SN approach is not suitable for determining the fatigue life. If the dimensions of the crack are known, we can instead determine the fatigue life using a linear elastic fracture mechanics approach. This involves calculating a critical crack size, which would result in fracture, and using a crack growth law to calculate the time required for the crack to grow to this critical size. But that's enough about fatigue for now. Stay tuned for more engineering videos.
The high ground. There is no substitute. The high ground is where vulnerabilities are reinforced or exploited. Time and again, whoever owns the high ground, the best intel, wins. Know what they want, know what they can do, know where you stand. The CrowdStrike 2020.
Okay, then we'll call up the day. It's already 4:45.
Okay, sir. Thank you.
Okay.